is it true like this reinforcement learning looks at a problem as a whole, which might not be the case for ML?
How the algorithm is rewarded and what you mean by a whole. That's really important here. The short but probably not satisfying answer to that question is that if the rewards and costs are based on the whole, then it will actually consider the whole. That is to say, if you're rewarding the algorithm to consider everything relevant to you in terms of the outputs of the system, then it would also consider everything relevant to you in learning and making its decisions. So all the features will also be considered, in sort of getting all of the outputs, right? You have to consider all of the features in the structure. Of course, rewards are a useful metaphor, and it's impossible to literally reward a machine. The machine is in reality just optimizing a function, but it is very helpful to think of it in terms of rewards. So concretely, Facebook's feed algorithm, for example, may or may not be a reinforcement agent, but let's pretend for the purposes of this discussion that it is, and that it is rewarded entirely based on human attention that is paid to its items in the feed. If these two conditions are met, then it would likely favor posts that are racist or otherwise bigoted. Why is that? Because they garner attention. So if someone says something outrageous, we will all be forced to pay attention to it. So then, to get back to your question, this algorithm would be a reinforcement learner which considers the whole, if by whole you mean everything relevant to attention, and it fails to consider the whole if you mean something different with this expression, such as the well-being of users, decency, etc. You would have to include those other things into the reward mechanism in a quantifiable way. And then those other considerations would also be considered by the algorithm. You see? In fact, the reward mechanism should specify exactly how the various considerations are to be traded off against each other and how they're complementing each other. So in economics, we call this specification a utility function. And in some numerical function, it is some numerical function that maps any configuration of valuable factors you value to one number that represents the reward you get from this particular configuration. So if you reward the algorithm with everything you value in the utility function, which correctly expresses how you are willing to trade off factors and how they complement each other, then it will mimic your values and it will learn how to serve them, most likely better and more faithfully than a human could. The art then is to express your values in the form of a reward function or a reward mechanism. And this actually is not trivial at all. What is special about reinforcement learning is that the target or the label is a moving entity, and that we are in a highly dynamic environment relative to other machine learning tasks that can only handle a static world. Of course, not all reinforcement learners are built equally either. In order to get such superhuman performance as an AlphaGo, you need very powerful algorithms as well. So it's not just the reward mechanism, but the reward mechanism is probably the trickiest thing. But you also need great neural networks or whatever the top algorithms are that currently do the best. However, I think that the most important thing is still to pay attention to the reward mechanism. If you get this one right, your algorithm is at least trying to solve the correct problem. And if you're not, then the best algorithm won't do any good at all. In fact, the better the algorithm is, the better it solves the wrong problem, which could be actually worse than having a not so good algorithm solving the wrong problem. So only hunt for the best algorithm, that's my advice, once you are sure that your reward is right. For the best algorithm, there are a lot of things you can try, and I would recommend just doing that, just trial and error. The same way as a reinforcement learner itself will do it then afterwards. It always depends on the use case. So start simple and establish a benchmark, and then only after that add complexity, and only if it is warranted in the sense that it significantly outperforms the benchmark model.